Okay, the exams overall were good. The average was good. Most people did well. There were two issues that came up a lot that I wanted to address. They're easy to fix. So two common issues on exam one. The first one was units. You don't have to follow the units through the calculations or anything, but you need to know what the units are at the end. And if your units are mismatched, your strain answers are just going to be plain wrong because the strains are unitless. So I would recommend before you do the calculation, just put everything in SI units. If it's given in gigapascals, that's that number times 10 to the 9th pascals. If it's given in megapascals, that's times 10 to the 6. So put everything in SI units. Before the calculations. And then at the end, if you want to change it back to gigapascals or megapascals or whatever, you can do that. Remember that mega means times 10 to the 6, and giga means times 10 to the 9th. So if you see like 7 megapascals, that means 7 times 10 to the 6 pascals. And so it's easy to go into SI units and then, okay. Anybody have any questions about units? Yes. Yes, that is. So yeah, so here are all the things that we know about. Stress is pascals. Young's modulus is pascals. Strain is unitless. Poisson's ratio is unitless. And traction is pascals. I think that's everything. So just express them like this, go through the calculation, and then if you want at the end, you can change it back. And then the second thing was just rancid, egregious round-off error. So a lot of people were writing, particularly the strain answers, with a single significant digit. So this is, the title of this is round-off error. If you give a strain value as 0.0002, okay, you're expressing that with one significant digit. Okay, so whatever precision you've put into all your calculations, you're boiling all of that calculation down to a single significant figure. And then if you're going to go from here and calculate new stuff, you've thrown away all the previous precision, and all that you have is a single significant figure to work with. And then if on top of that, you now do your calculations and express them with, go back to a usual like 4 significant figures or whatever, those last 3 significant figures are just random. You know, they don't have anything to do with the problem. So don't do it like that. Don't do that. Write it in scientific notation. So then this would be 1, 2, 3, 4. Say this is 2.316 times 10 to the minus 4. Okay. Then you're keeping 4 significant figures for your future calculations. Okay. So I had a lot of, people's answers were drastically different on these problems using the same things, and it was because at some step along the way, a lot of people just threw away all their precision except for one digit, and then chaos ensues. Yep. Okay. If your calculator, okay, on a TI-89, what you do is, well, it's basically always rounding if it gives it to you in this form, because none of these numbers are cooked in a way that's going to give you simple answers like that. So there's always more going on if you see it like this. On a TI-89, I know that so it gives you your answer. If you highlight that answer and hit enter, it'll list your answer out in the bar where you like enter new equations, and it'll do it in scientific notation there. I don't know how to do it on every calculator. If you want to talk about it, we could figure it out. But the bottom line is you need to figure out how to do it. Every calculator will do, there's no calculator ever made that is going to give your answer with one significant figure with no way to see anymore. Okay. Yes? Oh, okay. Yep. Oh, yeah. Right. Scientific notation is way better for strain. You don't want to write it in standard notation because it's so easy to miss one of the zeros or count the spaces wrong or whatever, And then, you're off by a factor of 10. And if you're off by a factor of 10, your answer is very, very bad. Okay. Any other questions? Okay. That's it on the test. Overall, yeah, it was really good. It seems like people are on the right path. So let's go back to principal stresses. And so the bottom line is for any stress tensor, there are 3 pairs of eigenvalue and its corresponding eigenvector. The eigenvalue is the principal stress, and the eigenvector gives the orientation of the corresponding face. So if you have for example, sigma 1, so say your first one is sigma 1, and let's call this V1. And then sigma 2, vector V2, and sigma 3 and a vector v3. Then the principal stress tensor is sigma 1, sigma 2, sigma 3 on the diagonal with everything else zeros. Where x is parallel to v1, y is parallel to v2, and z is parallel to v3. What if you don't want your x to be parallel to v1? You know, the calculator just spits out these pairs in any order. What if, for some aesthetic reason or whatever, you want your x-axis to be parallel to what they're calling v3, and their y-axis parallel to v2, and the z-axis parallel to v1? You don't even have to do that. You just still give the orientations of the x, y, and z axes, however you choose them. And you just reorder them with, you take your sigma 3 and put that here. And you put your, you know, and so this is x, y, z, whichever one you want to be aligned with it. That's how you decide where it goes in the matrix. That's right. Yep. Eigenvalues can be imaginary. They can be they're complex numbers in general. So what do we do if we get an imaginary answer for one of these? Well, in general, eigenvalues of a general matrix are complex, but a symmetric matrix, if you take the eigenvalues, they're real. Our stress tensor is always symmetric, and so our eigenvalues are always going to be real. Okay, so these, which is good because we don't have any meaning for an imaginary stress. Okay, so let's start to think through some of these things. So I'm going to start out with kind of a trivial example, but we'll see how it works. So say that our stress tensor is 3, 0, 0, 0, negative 5, 0, 0, 0, 0. So what's the principal stress tensor? And draw the coordinate system. You know, the principal coordinate system. Well, the meaning of a principal stress tensor is that all you have is diagonal elements. So this is already a principal stress tensor. So when we calculate the eigenvalues, we need to get those answers back, 3, negative 5, and 0. Yep. Yeah, because usually you're not gonna start with one that's only on the diagonal. You're gonna start with values everywhere. Yeah. And so yeah, then your principal values aren't gonna appear in your original matrix. Yeah. But we're starting here with a principal stress already. So our eigenvalues that we calculate are going to be 3, negative 5, and 0. Yes, that's right. That's what, think of that as the physical definition of principal stress, because the tractions on every face are normal, which means there's none of those off diagonal elements. Yep.
eigenvalue, why we didn't say x times? If there's any constant, why we just we call it eigenvalue for this like constant? You got the question?
No, can you repeat it?
So basically, so the equation is the fraction times the normal.
Yep.
Eigenvalue times the normal.
Yeah, that's right.
So basically, this eigenvalue, we say it should be an eigenvalue. Why we didn't call it like instead of saying this it is an eigenvalue, why we didn't like choose to be like any x or y or something that make it parallel? Why do we have to specify the eigenvalue? Does this gonna make it different?
Well, no, really, if you think about what that traction calculation does, that's exactly what we're specifying, is that we're looking for a stress tensor where all we have are diagonal elements. If you go back to that definition equation, that's what it says. It says it in kind of a roundabout way, but so anyways, in this one, we should get lambda equal to 3, -5, and 0. Right. When you find a coordinate system where your original stress is represented with no off-diagonal elements, all you have are diagonal elements, then that's your principal coordinate system, and those are your principal stresses. No, so we're going to go through the calculation with the lambdas, and we're going to get these values, and then I'm going to sort of show how to interpret that, okay? So we'll go to the eigenvalue equation. So we have 3 minus lambda, 0, 0, 0, -5 minus lambda, 0, 0, 0, 0 minus lambda. And we're taking the determinant of that and setting it equal to 0. Okay, that's how we're going to find those principal stresses, those lambda values. And so the determinant says the quantity 3 minus lambda times -5 minus lambda times negative lambda minus 0. You follow me on that? That's so to take the determinant, we have this times the determinant, this subdeterminant, minus this, well, that's 0, so whatever we're multiplying by is going to be 0, plus this times this subdeterminant, that's also going to be 0. So minus 0 times ... plus 0 times ... And so what we get is, this is the same thing as saying 3 minus lambda times 5 minus lambda times lambda is equal to 0. And what are the roots of this polynomial? Lambda is equal to 0 is 1. You know, you need, the only way to make this polynomial equal to 0 is to make one or more of these factors equal to 0. So if this one's equal to 0, lambda is 0. If this one's equal to 0, lambda is 5, -5. Should be plus. So if this one's equal to 0, lambda is -5. If this one's equal to 0, lambda is 3. So lambda is equal to 0, 3, -5. Any questions about anything I did there? So I just set up that, it's called the characteristic equation. I just set up that polynomial equation, found the roots, and those are the eigenvalues. And now one by one, we're going to plug those eigenvalues back into the eigenvalue equation to find the eigenvectors. Yeah, but I want to, my reason for doing this is setting us up for real ones, but yes, yeah, you could just multiply them together. So the corresponding eigenvectors. So first I'm going to do it for lambda equal to, let's do 3 first. Okay. So our eigenvalue equation says 3 minus lambda, 0, 0, 0, negative 5 minus lambda, 0, 0, 0, negative lambda, times this normal vector, nx, ny, nz, equal to zeros. And so if I put in lambda equals 3, 3 minus lambda is 0, 0, 0, 0. Negative 5 minus 3 is negative 8. Negative lambda is negative 3. And now doing the matrix multiplication gives 3 equations. The first one says 0nx plus 0ny plus 0nz is equal to 0. So the first one says 0 equals 0. The equation in the second row says 0nx minus 8ny plus 0nz is equal to 0. And the third equation says 0nx plus 0ny minus 3nz is equal to 0. So what's a unit vector that meets these 3 criteria? So 2 unit vectors meet these conditions. And y has to be 0, and z has to be 0. What are the possible unit vectors? That's not a unit vector, though. 1, 0, 0, and negative 1, 0, 0. Okay, so the face corresponding to the eigenvalue of 3 has to be positive in our original positive x-axis or negative x-axis. Okay. Now the second one, for lambda equal to negative 5. Yeah, so remember, we got this equation by putting lambda equals 3 into this. Okay. And so this 3 corresponds to whatever unit vector we get in the calculation. So the 3 is the traction on the face with an outward facing normal either in the positive x direction or the negative x direction. Yes? Yep. Right. Well, there just are only two possible vectors that have a length of 1 and have y and z components equal to 0. Those are 1, 0, 0 and negative 1, 0, 0. You can try anything else you want, 56, 0, 0. That meets those conditions, but it's not a unit vector. Okay, so now lambda is equal to negative 5. So we have 3 minus negative 5 is 8. And then we have negative 5 minus negative 5 is 0. And then we have 0, 0, 5. Okay, so that's the eigenvalue matrix that we get by plugging in negative 5 for lambda. And that times our unit vector is equal to zeros. And so the equations we get here, the first equation says 8nx is equal to 0. The second equation says 0 is equal to 0. And the third equation says 5nz is equal to 0. So what unit vectors meet these conditions? 0, 1, 0 and 0, negative 1, 0. So those are the two options for the outward facing normal corresponding to lambda equals negative 5. Yep.
So I feel like it seems that because we have an x, we have like values, we don't have equation for y, we choose it to be 1.
Well, yeah, I mean, in order, we know that our final vector has to have a length of 1. And so if the other two are 0, all you can have is a 1 or a negative 1 in that third remaining component. Okay. Yeah, right. And then the third one, we could go through that calculation again, but lambda equals 0. There's only one direction left that's perpendicular to the other two. And so that has to be 0, 0, 1. And 0, 0, negative 1. The third one, you can use the cross product. Yep, that's right. So yeah, so now a bunch of coordinate systems work. We could say the principal stress tensor is equal to 3, 0, 0, 0, negative 5, 0, 0, 0, 0. And the coordinate system is that, where our x-axis is what our original one was, our y-axis. Or we could say our principal stress tensor is 0, 0, 0, 0, 3, 0, 0, 0, negative 5. And now we could have our x-axis pointing. So remember that 0 eigenvalue, the 0 principal stress, corresponded to an axis in line with our old z-axis or opposite our old z-axis. So let's make this our x coordinate now, our x-axis. The 3 corresponded to a coordinate axis parallel to our old x. Okay, that's what we got, 1, 0, 0 or negative 1, 0, 0. And so let's make our y-axis like this. And then x cross y has to be equal to z. The third one is like this. So there's a whole bunch of, there's always going to be this non-determinant thing about it. You have a bunch of choices for your orientation, but you have to make the eigenvalue line up with the correct axis, and you have to make your coordinate system obey the cross product rules for coordinate axes. Okay, we're not really going to do much of that, but that's how you figure out the orientation of the principal coordinate system. Mostly, we're just going to want the values. Yep, and then we also want this max shear value. And so that is going to be equal to the maximum principal stress minus the minimum principal stress over 2 absolute value. So that's 3 minus negative 5 over 2, so 4 megapascals. So no matter what coordinate system you choose, you could never find a shear stress bigger in absolute value than 4. And if we wanted the stress tensor, we'd want to transform the principal stress tensor to a coordinate system rotated 45 degrees about the middle axis. Okay, so say that our coordinate system is 3, 0, 0. So let's say our principal stress tensor is 3, 0, 0, 0, negative 5, 0, 0, 0, 0. What axis corresponds to the maximum? X. What corresponds to the minimum? Y. So we want to rotate 45 degrees out the z-axis. Always 45 degrees. What? It's boring? Yeah. Yeah, right. So the rotation matrix then is, this is 45 degrees about the z-axis, 7071.70710, negative 0.7071, 0.70710, 001. And so the stress tensor with the maximum shear is that Q times the principal stress tensor times Q transpose. And if you do that, can someone do that? Anybody have it programmed? Go away. Okay, -1, -4, 0. 0, 0, 0, right. Okay, so this is a stress tensor where the maximum shear in absolute value is 4 megapascals. So this fact that the maximum shear is at a coordinate system oriented 45 degrees about a normal stress, you see this 45-degree relationship in compression fractures. Well, you see it in engineering materials too, but you see it in bone fractures. This is something orthopedic surgeons are used to seeing. Fracture. So if you have a compression fracture of the leg, which is something that happens a lot in car accidents, so your car crashes, your heel hits the underside of, like where the pedals are, you get a compression fracture of the leg where the femur is loaded so there's the femur, and it's loaded in compression like this. And the way the fracture happens is like that, exactly 45 degrees from the line of compression. And the reason that happens is because it's the shear stresses that cause this fracture. I don't really know. I don't really have a description like that of it, but it's a well-known pattern. Always 45. Yep. And you always find it by rotating 45 degrees around the middle axis. In other words, you're rotating to right in between the maximum and minimum normal stresses. Yeah. 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 Let's just do a few more examples, okay? So let's just keep going. So in this case, a stress element would look like this. Your principal stress element would look like this. And so you'd have some negative value and then 0, 0. And so you'd rotate about one of the two zero axes, either one. Yeah. All right. So now let's say that original stress tensor is 1, 9, 0, 9, 1, 0, 0, 0, 0. So first, what are the principal stresses? Listed from the maximum one to the minimum one. What's the maximum shear stress? And then we'll calculate the principal stress tensor and the principal axes. And actually, let's also calculate the stress tensor with the maximum shear. Okay, so A and B are by far the most commonly useful things here. Those are the things you're going to always calculate. And those are the easiest ones to do. So first, for A, on a calculator, you'd type in so that's the command on a TI-89 calculator. It's like eigvl for eigenvalue. And your argument would be that original matrix. So 1, 9, 0, semicolon, 9, 1, 0, semicolon, 0, 0, 0. And it'll just spit out these three values, 10, -8, 0. So in order from maximum to minimum, that's 10, 0, -8. Done. If you don't have a calculator that does it, well, there are other things, even if your calculator doesn't do it, like on homework and stuff. Wolfram Alpha does it online. MATLAB does it. So there's no reason to do this, to do this by hand if you need these values. But you can also set it up as a polynomial, and then you'll end up using the quadratic formula to solve it. So by hand, this would be 1 minus lambda, 9, 0, 9, 1, 0, no, 1 minus lambda, 0, 0, 0, minus lambda. Set the determinant equal to 0. That gives a polynomial, and the roots are the eigenvalues. In this case, the polynomial would be 1 minus lambda. 1 minus lambda times the quantity, 1 minus lambda times negative lambda minus 0. And then minus 9 times the quantity, 9 times negative lambda minus 0 plus 0 equals 0. Multiply it out, you get this polynomial, solve it. You can factor out the lambda, that's your root equals 0. Okay, so now what's the maximum shear stress? Well, Tmax is just equal to sigma max minus sigma min over 2, which is 10 minus -8 over 2, which is 9 megapascals. And for most purposes, that's all you need to do. That's all you need to know about it. But there's also the more complicated stuff you can figure out, the orientation of the coordinate system, the principal stress tensor, and a stress tensor where you have maximum shear. So that's the next stuff we're going to do. Any questions about those the two key things? If you can do those two things, you'll be doing 90% of what you ever need to do with eigenvalues with principal stresses. Okay, so C. What did I say was C? So now we're going to calculate the principal stress tensor. Well, that by itself is easy. We can put these three in any order we want. I guess I'm going to do it as principal stress tensor is equal to 10, 0, 0, 0, 0, 0, 0, 0, negative 8. Just put it in order from max to min. Now we have to come up with a coordinate system that matches this. So we're going to come up with axes corresponding to each of these eigenvalues. And to do that on a calculator, you type EIGVC, like eigenvector of that same matrix, the original matrix. And it'll give you 0.7071, 0.70710, negative 0.7071, 0.70710, and 001. And each of these is plus or minus. So you have to choose the plus and minus so that it's a sensible, an acceptable coordinate system. You can't have x cross y equal to negative z, for example. These are listed in the same order as that function eigenval. Okay, so if your eigenval function listed them out 10, negative 8, 0, that means that this one corresponds to 10, this one corresponds to negative 8, and this one corresponds to 0. And let's go through the next two parts on Friday. But so far, everything, if you have a calculator or a computer program that does this stuff, which everyone has access to on Wolfram Alpha online, nothing's taken any work yet. It's just been punching that matrix into a program or a calculator. But I'm going to show you how to do it by hand too. Yep. The original coordinate system. Yeah, that's an important question. Yeah, so these, like, what do these mean? That these tell you the principal coordinate system? It means in your starting coordinate system, one where you gave that original stress tensor, the new principal coordinate axes are associated with those. Any other questions?